factors that affect the frequency of the standing wave set up in a string. So there's three main ones that we need to talk through. First one is the most obvious one, the length of the string. Thinking about what that wave looks like. The waveform on the string is always an integer number of half wavelengths, like it's 1/2 wave or a whole wave, or 1/2 or 2.5. It's always an integer number of half wavelengths. So as we make the string length longer, we must make the wavelength longer. And so the most obvious factor that affects the frequency that the string resonates at is just the length of the string. The next one is the weight of the string. The weight of the string, what we really mean is how much mass is there per metre length, per unit length of the string. So we can kind of define this mu as mass per unit length, just mass divided by length. And what happens is that as the string gets more massive, there's the same restoring force trying to pull it back to the centre when you pluck it. But if it's more massive, that same force is going to cause lower acceleration. So the string is going to take longer to accelerate back to the centre. Slower time means lower wave speed travelling through the string. And so as that wave speed decreases, V equals F lambda, and so the frequency must decrease too. And then the final factor is the tension in the string. That's how hard we're pulling it. The tension force is the force that's pulling the string apart. And the tension force must be the same at any point in the string. As that tension force increases, that's kind of doing the opposite as the increasing the mass. As the tension force increases, that means we're pulling the string back harder back to the centre, greater acceleration, and that means it's going to get back to the centre in less time when we pluck it. Wave speed increases. So as the tension force increases, the wave speed increases, V equals F lambda, and that means that the frequency must